Hi, this is Stephen Brower from Rat Valley Community College. This is our Introduction to Graphs to accompany the Data Structures course. There are slides in Canvas, and some of the stuff you're about to see is the same as the slides in Canvas. There are different examples on, well, they're not exactly the same. Let's put it that way. So, graphs. A graph consists of nodes and edges, also known as links, or links also known as edges, and they're grouped together. Now, up to this point, we have been using the data structures as mainly as a collection of data for holding on to data in a particular way. So a linked list was holding on to the data, stack was holding on to the data in a particular way. Last in, first out. Queue was holding on to the data in a particular way. First in, first out. Tree was holding on to the data in a particular way. Well, we did binary search tree, and so it ordered the nodes that were coming in. Graphs, their intention isn't necessarily to hold data. Their intention really is to talk about sort of the connections that can be formed between things. So depending on the application that we're using it for, then it's more the connections, it's more the edges that would be more of interest. Well, the edges are connecting the vertices, though. What I'm getting at is, you know how project 2 was a linked list of objects, and project 4 might be a tree of objects. We're not going to do a graph of objects, not as a way of collecting data. That wouldn't work that way. So the use of a graph would be a little bit different. I have some applications in a couple of slides. I just want to get through some terms. Paths. A path would be a collection of edges that can be followed to get from one node to another. So V2 to V0 along this edge, then along edge 1 to get to vertex 1. That would be the path V2 to V0, V0 to V1. So that's what just happened there. Another path would be going along this way through V3. V2 along this edge to V3, along this edge to V1. And so those are two different paths going from vertex 2 to vertex 1, two different ways of getting there. There's other ways, but let me just show you one of the other ways. Vertex 2 along this edge to vertex 0, then along this edge to vertex 3, then along this edge to vertex 1. Again, another path that can be taken to go from vertex 2 to vertex 1. So a path would be the collection of edges that can be followed to go from one node to another node. Adjacent versus reachable. Two nodes are said to be adjacent if there's an edge connecting them. So V0 and V2, V2 and V0, there is an edge connecting the two of them. So like from V2's perspective, we say V0 is adjacent. From V2's perspective, vertex 3 is adjacent. But from vertex 2's perspective, vertex 1, there's not an edge that goes directly there. That's not adjacent. This will have an effect, or this is an important consideration for later when we get to an adjacency matrix, where an adjacency matrix keeps track of adjacencies. And vertex 2 is not adjacent to vertex 1. Vertex 1 is not adjacent to vertex 2. But the idea of being reachable, that from vertex 2, vertex 1 is reachable because we can get there through one of several paths. Vertex 2 to vertex 0, vertex 0 to vertex 1, so therefore vertex 1 is reachable. Vertex 2 to vertex 3, vertex 3 to vertex 1, therefore vertex 1 is reachable. Vertex 2 to vertex 0 to vertex 3 to vertex 1, therefore it's reachable. And yes, vertex 2 to vertex 3 to vertex 0 to vertex 1 is reachable. What we want to avoid are cycles. A cycle would be vertex 2 to vertex 0, vertex 0 to vertex 3, vertex 3 back to vertex 2 again. That would be a cycle, and cycles are things that we want to avoid because in a sense we're not making any progress. If we're trying to get to vertex 1, looping back around to ourselves to vertex 2 isn't helping us get any closer to vertex 1. We look at graphs that either can be undirected or directed. With an undirected graph, there are no arrows to the edges, and you can go both directions. Meaning we can go from vertex 2 to vertex 0. We can go from vertex 0 to vertex 2. We can go from 2 to 3. We can go from 3 to 2. So with undirected graphs, we can go in either direction along the edge. So vertex 0 to vertex 3, vertex 3 to vertex 0. Directed graphs, also known as a digraph, there are arrows, and you can only go in a particular direction. So vertex 0, we can go to vertex 2, but along that edge, we can't get back to vertex 0 because the arrow, since it's going from 0 to 2, we can't get there. So from vertex 0's point of view, vertex 2 is adjacent. From vertex 2's point of view, vertex 0 is not adjacent, but vertex 0 is reachable because we can go vertex 2 to vertex 3, vertex 3 to vertex 0, and we now reached vertex 0, or we can go vertex 2 to vertex 3, vertex 3 to vertex 1, vertex 1 to vertex 0, and then it's reachable. Weighted graphs. There are values. Well, let me talk about the example. If we think of us at home connecting to our internet service provider. Now I'm doing here the DSL idea, not the cable modem, but the download, there is a speed of which we download, and so if the bigger files we're downloading will take a little bit longer than the small files, but for us doing the download, there is a cost that is involved, and that can be represented either as speed or can be represented as time. And I do have this here as 3 megabits and megabits per second, and you may have a connection that's 25 megabits per second, which is faster. But if we're looking at download speed, we might just talk about the time. So if we have a 3 gig file, how long is it going to take to download it? It'll be a longer time downloading at 3 megabits than it would be at 25 megabits. And part of the reason why I'm splitting hairs on these two is something we're going to get to later, which normally would be next week, but now it's not next week, but later this week, is the shortest path algorithm. And in that one, we try to minimize the costs. So although speed is something that we want to maximize, if we think of it in terms of time, we can then minimize it. But some other examples associated with weight could be things like money. So if you're flying from, if you're flying from Newark to Los Angeles, there is a money cost with that flight going from New York to Los Angeles. There also is a time involved. And if we did legs, so if we went New York to Chicago, Chicago to LA, being that we had to land, have a layover, and then take off again, some time would elapse. So with weighted graphs, the edges have some sort of cost associated with them. And in reality, and I just gave the example of the flying, it could be two things. It could be money and it could be time. And so if we're looking at flying to LA, you either might want to fly to LA and say, I want to get there as quickly as possible, or you might say, I want to get there as cheaply as possible, or you want to do both. I want to get there as quickly as I can for the least amount of money without spending too much money. Okay, so weighted graphs, there's a cost associated with the edges. Some other definitions. That example that we just did, there were multiple edges, meaning that there was between these two nodes, there are two edges that connect them, in this case being directional, but there are two that connect them. A loop is an edge that connects the vertex to itself. And it may seem kind of silly, but if we are talking about flying out of an airport, suppose we go and get on a plane, we take off, we turn around and land in the same airport again. Well, that's going to cost us money. That's going to cost us time. But all we're really doing is leaving the airport and then landing again. When it comes to implementing graphs, and we'll get to implementation in a little bit, simple graphs are, well, simpler to implement. And a simple graph is a graph that has no loops, so none of these, and no multiple edges. And with simple graphs, we can use simpler intended data structures to represent them. What I want to show here are a couple of examples of where graphs are used. And so this would be the states that a process can be in. So it's like when you launch a process, initially it's on hold until it becomes ready for the operating system to run. Then there's going to be a ready queue. These are all the processes that are ready to get a slice of the CPU. And when finally the CPU is ready to run something, it takes whatever at the front of the ready queue and puts that into a running state. Now, what will happen with the CPU is that process will get a certain slice of the CPU in terms of time. You know, so many cycles it'll run, and then what it'll do is say, okay, time out, we got to give a chance to someone else, and then that process would then go to the back of the ready queue again. And so this can keep going on where we're going to running, we come back to ready. We go into running, we come back to ready. It actually happens so quickly that we don't necessarily perceive that this is happening, but the processes that are running are getting slices of the CPU. Well, when it's running, if it suddenly needs something from, let's say, the hard drive, it may put in a request and say, okay, well, when the data is ready, let us know. And then it puts that process into a waiting state. And then when an interrupt comes back saying that, hey, the data is ready, it can go out of the waiting state back into the ready and waiting until it goes back into a running state. And once a process finishes running, then it goes into the finished state. So this is a graph. There are nodes here. In this case, these nodes represent states that a process can be in. It can be ready, it can be running, it can be waiting, it can be finished. And then the paths would be how it gets from one state to another, or going from one state to another. So from ready to running, and then it can go from running back to ready, ready to running, then it can go from running to waiting, waiting to ready, and then finally finished. This is a partial diagram because the full diagram would be too darn much. But imagine a vending machine. And when we first approach the vending machine, there's nothing in there. We're at the zero balance. And well, if I stick in a penny, it spits it out. And we're still at the zero state because it doesn't recognize that as a valid coin. We're still in the zero state. If I put in a nickel, I'm at the 5-cent state. When I was at the very beginning, if I put in a dime, I'd be at the 10-cent state. A 10-cent state. And then if I was at zero and I put in a quarter, I'd be at the 25-cent state. And so what each of these states would have is, let's look at, one way to get to 25 state is we can put in a quarter. Another way that we can get to it, we can put in a dime, which will get us the 10-cent state. You can put in a nickel, which will get us the 15-cent state. We can put in another nickel, which gives us to the 20-cent state. I'm infatuated with steaks right now. And then another nickel would get us to the 25-cent state. So graphs are used to represent sort of state diagrams where the nodes would be the states that we're in. The edges would be, it might be a value received or some action that will take us from one state to another. Now, later we're going to look at a shortest path algorithm, and since I'm at 14.5 minutes, I'm going to be ending this one soon. We'll pick up on this on the next one. Yeah, I'm out of time. Let's go to part 2.